Good morning, everyone. All right, let's start. All right, so we were pretty split there, but yeah, osmium tetroxide, that is a syn addition. Both the oxygens come in one step. Hydrogenation, that's also syn. Both the hydrogens come in the same step and on the same face. But bromination, the bromine electrophile comes in at the top, bromine nucleophile comes in at the bottom. That is the only one that is anti-addition. So good job, Rachel, Nick, and Jeremiah. Good job. All right. Let's see. All right, so we are working on our learning checks. We're close to getting finished. We might finish this today or on Friday, which means your next problem set is coming soon. So this next problem, it's multi-step reaction sequence. As I said, we have to show stereochemistry. We have to consider stereochemistry as we go through. But let's look at each step separately. It's good for you to do mechanism. It's not required here, but it is good for you to do it because that will help you to figure out the course of the reaction. So if I make that one my electrophile, then I can break this bond and attack that carbon. I'm going to call this 1, 2, 3, and 4. So when I draw my product from that first part of the reaction, remember we're going to get a bromonium ion, and I need to show stereochemistry with that isopropyl group. So with the isopropyl group, I can do either wedge or dash. I'm going to do wedge here. It doesn't matter though. Why doesn't it matter? Because it's both wedge and dash, right? This is racemic. So it's both things. Now I do have the bromide that I formed, but I also have water. I'm not running the reaction in tetrachloromethane. So I need to, carbon tetrachloride is another name for that. But I need to do this reaction with the water as my nucleophile, not with the bromide. So I have a positively charged three-membered ring. And so with a positively charged three-membered ring, remember, we're going to attack the more hindered side. More hindered side. When I attack carbon 2, I have to break this bond. Don't forget that second arrow. But now I have carbon 1, 2, 3, and 4. Oops, sorry. Actually, I'm doing this wrong. Sorry. I was thinking about something else. All right, so anyway, we are attacking that carbon. So I have carbons, carbon 1 is still bonded to bromine. But carbon 2 now, I have inversion of configuration, right? This is an SN2 step. So I have oxygen down here, and I pushed this carbon-3, carbon-2 bond. And remember, there is a hydrogen there also. I push those two up. So I end up with up, isopropyl on the wedge, and hydrogen on the dash. Now remember, I don't have to show the hydrogen. I'm just showing that so that you guys can keep track of what's happening with stereochemistry. But the two things pointed down got pushed up, and oxygen now has its two hydrogens on it, one lone pair, positive charge. So what has happened? Middle of this bond to the oxygen. Where now this is an OH. So up here, I still have this isopropyl and this hydrogen. So my longest carbon chain here, minus H plus, I'll write here. My longest carbon chain, 1, 2, 3, 4. I want to redraw that. So 1, 2, 3, 4. I want to redraw it like this, where I keep all those carbons in the plane. And now up here at the top on carbon 2, I have two things. I have that hydrogen and I have the oxygen. So let me draw in the two things. But remember, I only have to really show the bond to the OH and show the stereochemistry there. But I'm going to have both. So as we look at this, let me get my model kit. So as we look at this kind of stereochemistry, remember, if you make a model like this, where you have just 3 different colors on one carbon, 3 different colors on the other carbon, that could help you to visualize this. So what we have here, I'll do these as the 2 groups at the top. So I have isopropyl and I have hydrogen and I have OH. So I'll do it this way. I have hydrogen in the back. I have blue as the isopropyl, and we'll do purple as the OH. So isopropyl, I want to move that. It's up at the top and pointed towards you. I want to move it down. And so as I rotate it from the front to down in the plane, now I have 2 things up at the top. So again, look at how we have this. We have this in the back, this in the front, and I want to rotate this down to being in the plane. So the one thing down, and then I have 2 things at the top. So coming towards you is the hydrogen, and going away from you is the OH. So I end up with the OH on the dash line, and I have the hydrogen on the wedge. So you need to have your molecular model. If you can't visualize this, you need to build your model so that you can visualize how you are rotating things. So we're rotating this, basically what is here, we're rotating it from the top and the front down here to the bottom. So as we do that, we're rotating everything around. The other way to draw this, because again, we don't need to show the hydrogen there. The other way to draw this would be to just show we have this OH as a dashed line, which assumes the hydrogen is on the wedge. So that is our intermediate after step 1. All we've done is step 1. Now we have to move on to step 2. So I'm just going to draw it down here. You can keep going with what you have, but I'm going to show this oxygen-hydrogen bond. Why do I need to show that bond? Because the next step adds in sodium hydroxide, so we know it's the hydroxide that is reacting there. The hydroxide, not the sodium. We know it's the hydroxide that is reacting. So we have a base, and we know that alcohols are acidic. So we go pick up this proton. Electrons are being pulled toward the oxygen. That's what happens in step 2. So we end up with still on a dashed line, but now the oxygen has 3 lone pairs and a negative charge. So what did we lose here in this step? We lost water, right? We made water. So every step that we've been going through so far has been racemic. We started off with this racemic starting material, racemic intermediate, and then here, everything here, we're just redrawing it in 3 different ways, right? This is 3 different ways of representing the same molecule. So I'll just write racemic here because it's 3 different things. They're all the same though. Again, here, racemic and racemic. So I drew this with a dash line for this oxygen, but it's just as likely that it would be the wedge for the oxygen, right? The other enantiomer is just as likely. All right, so we have an oxygen with a negative charge. We have a carbon with a partial positive because it's bonded to bromine. So what can we do? Well, we can attack that carbon, leaving group leaves. So we're doing an SN2, but really we're doing a Williamson ether synthesis. Really, we're doing a Williamson ether synthesis. So what do we get in the end? Well, again, this is 1, 2, 3, 4. One, two, three, 4. We get this oxygen carbon bond, which forms a 3-membered ring, so we make an oxycyclopropane. With our oxycyclopropane, though, we need to show the stereochemistry. So remember, this 2 oxygen bond that we had initially, this bond is a dashed line. And so as the oxygen comes into attack, it's going to attack on the same face. And so we get both of these as dashed lines. But what do we like? We like to have, if we have this 3-membered ring, we want to have the isopropyl group as the thing that's coming in the plane or out of the plane. So we really want to redraw this. Where we put the isopropyl either in the plane or out of the plane. What do we have here? Well, up top, we have a hydrogen. Up top, we have a hydrogen. And we want to rotate it, right? In the back, we have the oxygen. We want to pull it forward. And so if we pull that oxygen forward, then that hydrogen pops down to the bottom. So we still have a hydrogen, but now it's at the bottom. As we do that rotation, if we move this oxygen kind of forward, moving that forward, then the hydrogen goes down, but still in front, and the isopropyl gets pushed to the back. So isopropyl's in the back, hydrogen's in the front on that carbon. And so here on carbon 1, we know we don't really have to consider carbon 1 because it's just 2 hydrogens. So we're just putting those 2 hydrogens, one's on a wedge, one's on a dash, but it doesn't matter. But again, this is racemic. All right, we've done step 2 now to get our oxycyclopropane. Now in step 3, you know that the other thing here would be like diethyl ether or THF because you have an alkyl lithium reagent. So with our alkyl lithium reagent, one, two, three, 4. What do we know about these? Well, we know partial negative, partial positive, right? They're the same as a Grignard. They are strong bases but good nucleophiles. We want them as a nucleophile. Now, there's no positive charge on the oxycyclopropane, right? The oxycyclopropane is neutral. So when the 3-membered ring had a positive charge, we said we would attack the less hindered side. But now we're going to attack, oh, sorry, I meant more hindered. We're attacking the less hindered now. We attacked the more hindered side before. Now we are going to attack the less hindered. So from the middle of the bond to carbon 1, and then we break the oxygen carbon 1 bond. Neutral, we attack the less hindered side. Positive charge for the ring, we attack the more hindered side. So I'm going to call this carbon 5, and I'm going to call this carbon 6. Which two carbons are making a bond to one another in this new structure? Please tell me that in the chat. Which two carbons are forming a bond in this new structure, this product that we're going to get here? I'm forming a bond between carbon what and carbon what? So put those two numbers into the chat, please. Exactly, 6 and 1. So I have my carbons 5 and 6. So here's 5, here's 6. And then I have 1, which is bonded to 2, which is bonded to 3, which is bonded to 4. So between 2 and 3, we still have it on the dash line. Because, yeah, this is an SN2, but the SN2 isn't happening at carbon 2. The SN2 is happening at carbon 1. What else is attached to carbon 2? Carbon 2 has this oxygen that now has a negative charge. So then our last step, aqueous workup step, go and pick up a proton. Here's our product. But is this good? No, we want to redraw this to where we get, so 5, 6, 1, 2, 3, and 4. We want to get all those carbons in the plane. And so what we want to do is get the OH either coming out of the plane or going into the plane. So what do we have? We have this isopropyl group that's in the back. We have a hydrogen in the front. We want to nudge the isopropyl to the front, to the middle more so. We want to nudge the isopropyl to the middle. It's in the back. We want to nudge it to the middle. And so as we do that, we have here a hydrogen that's down low. We want the hydrogen now up high. And so as we do this rotation, a slight rotation, we end up pushing the OH to the back, and our hydrogen ends up in the front. We end up pushing the OH to the back. So here in this reaction, what are we getting for our product? Well, we are getting this, but it is racemic. So that means that we also have this product. Both of these products are formed. One-to-one mixture, right? Racemic for this. So we get these two products. You can draw one and write racemic underneath it, or you can draw both and write one-to-one or enantiomers or something along those lines. Questions on this?
I have a question about step 1 with the bromine.
Uh-huh.
So why do the methyls on the wedge detach?
The methyls on the wedge, why did they
Or
detach?
the two coming out of on carbon 2?
They're still there. They didn't detach in step 1.
Or like where it says racemic, or like the two products, why did the
This,
second? Yeah.
we still have all the same carbons, 2, 3, 4. We still have the same carbons, nothing detached in the course of the reaction. All we did was rotate. So we're talking about here in this structure, in this one here.
Yeah, I can't see the other one because there's a gray square in front of it, but oh, there we go. Like the second one, like where did the methyls go on that one? Because they just turned into.
This is the
Oh,
methyl.
actually, I get it now. I'm sorry.
It's a hydrogen.
It turned
They're
into,
just close
okay,
together. Yeah. So
those aren't the same. Okay, that makes more
yeah.
sense. And then also, you just decided not to write the sodium, right? Because it's a spectator.
Right. We can write it, but it's not doing anything. So I just want to reiterate because I see a lot of people try to do things where they're like, "Oh, sodium's here now." No, it doesn't react. Don't have it react. It doesn't do anything. It's just an ion that's floating around.
Okay, thank you.
Uh-huh. Other questions?
When we're doing a reaction like this, do you want us to put racemic under all the steps that are racemic or just at the end?
You can put it at the end. You just need to understand that they are racemic. If they are racemic, they're not always going to be racemic. So you have to think about, are they racemic?
Okay, thank you.
Other questions? All right. So let's move on. So here on this slide, there were two, same starting material, but two different reaction conditions. So here's our first one, which is MCPPA, which is a carboxylic acid. So what is our mechanism here? So you should for sure be able to write the mechanism for any of the things that I show you the mechanism on. So partial positive there, partial negative. From the middle of this bond to this oxygen, because it is electrophilic, middle of the bond into the middle of that bond, middle of this bond to this hydrogen, and then middle of this bond to one of the carbons. So notice that I drew this kind of below the alkene. And so if I drew this below the alkene, I'm going to draw my three-membered ring with that oxygen also below the alkene. If I go back here, I drew this whole thing at the top above the alkene. So up here, this is above the alkene, which is why I drew this up high and I drew the isopropyl down low. But on this one, I'm going to draw this oxygen down low, and I'm going to put up high my groups that are attached. So the isopropyl and the ethyl are both on the same side, so I can do them both as a wedge or both as a dash. Either one is fine. I'm going to do them both as a dash. And so then this methyl ends up as a wedge. So this would be my intermediate after step 1. So after the MCPPA, we get an oxycyclopropane. We have to show the stereochemistry, and this is racemic. So opposite stereochemistry, where the isopropyl and the ethyl are a wedge, and the methyl is a dash. That would be true as well, a one-to-one mixture of the two. All right, now in our next step, we add an acid. What happens here? Well, oxygens do what they do. They love to pick up protons. And so it picks up a proton and becomes now an oxonium ion, oxygen with a positive charge. But nothing changed with our stereochemistry here. All we did was protonate. So we protonated that. That's now a good leaving group. And then we have water, right? We had acid and water. So the water comes in on the opposite face to where the original oxygen is. So this oxygen was our original electrophile. And now this oxygen is now our nucleophile. Yeah, it's a poor nucleophile, but it is our nucleophile. So the nucleophile is going to attack on the opposite face to where the electrophilic oxygen was. And as it attacks, is it going to attack the more hindered or the less hindered side? Can you put more or less into the chat, please? More hindered or less hindered side? We're going to attack the more hindered side. So we're going to attack here, and we're going to break this oxygen-carbon bond. So what's going to happen here? Well, nothing changes here, right? That's still a dash, that ethyl. And we're going to have our original electrophilic oxygen attached to that carbon. This was our original electrophile. But as we do this reaction, it's an SN2, so inversion of configuration. We're going to end up with our two groups up here at the top now. One is on a wedge, one is on a dash. What's on the dash? Still the isopropyl. What's on the wedge? Still the methyl. But now we have our new oxygen added there. So our oxygen that was the nucleophile. So then our last step is to deprotonate here. So minus H plus. And so we end up with this product. So what happened here? Well, looking at this, if we number this, we said this is our nucleophile, this was our electrophile originally. That's where how they came in. Our nucleophile came in, our electrophile came in. If we number this, we'll go 1, 2, 3, 4, 5, 6. We're adding these oxygens to carbons 3 and 4. Right? We added the oxygens to carbon 3 and 4. We added our electrophile to carbon 4. We added our nucleophile to carbon 3. Remember that this is a Markovnikov addition. The electrophile goes where there are more H's. We know that there's one hydrogen on carbon 4. The electrophile goes where there are more H's. The nucleophile goes where there were fewer H's. So this is a Markovnikov addition where carbon 4 got the original OH that was the electrophile. All right, so we're not done with this, right? We want to get carbons 1 through 6 in the plane, but we're showing that this is a Markovnikov addition and it is an anti-addition. We can see both of those things, Markovnikov and anti. They're added on opposite planes. The electrophile goes where there are more H's. So then we need to have carbons 1 through 6, 1, 2, 3, 4, 5, 6. In the plane. And so what we need to have now on carbon 3, we have two things. We have a methyl and we have an OH. On carbon 4, we have an OH. We need to figure out how we're going to rotate this. So we have in the beginning this isopropyl that's down below, but now it is in the back. So we want to nudge it forward. We nudge it forward into the middle so that it's in the plane. As we do that, the methyl gets pushed to the top and in the front, and the OH gets pushed to the back. If you can't visualize this, make your model, just like I showed you with the different colors. And then on carbon 4 now, we have this ethyl that's in the back. At the top, we also have a hydrogen. There's also a hydrogen there at the top. And so we want to nudge that forward, the carbon 5-6 bond, we want to nudge it forward. And as we do that, the OH ends up in the back and the hydrogen ends up in the front. This is our final product. And yes, this is racemic. So the opposite stereochemistry at carbon 3 and carbon 4. is also a likely product. Both of them are equally likely. Questions there? So MCPBA is anti-addition. But now we have osmium tetroxide. We already talked about osmium tetroxide, right? We said this is a syn addition. We talked about that at the very beginning. And so let's number these carbons again, same exact starting material. And let's draw the mechanism. So osmium tetroxide, we have our osmium with 4 double bonds to the oxygens. We attack one of the oxygens, we move electrons in onto the osmium, and then from the next double bond, we attack the other carbon of the double bond. Again, we're doing this from the bottom, so I'm going to do oxygen, oxygen, osmium. Down below, I'm going to put a lone pair on the osmium and then a double bond, another double bond. Osmium can hold more than an octet. It's fine. So same as we had before. I'm going to do this. So exact same way that I was doing it before. So you need to know the mechanism for the first step, but the second step, H2S, no mechanism needed. You just need to know that these bonds get broken. These oxygen-osmium bonds magically get broken, and we end up with OHs instead. And nothing changes with our stereochemistry that we established in that first step. So you can see both oxygens get added in step 1, not in 2 steps. Both oxygens come in step 1. This is a syn addition. We can see here that is a syn addition. But now we need to rotate this just like we did before in order to get all of our carbons, 1 through 6, in the plane. So same as before, we need to do some rotations around these bonds. All right, so looking at this, we need to move, let's move 5, 6, let's just nudge it forward. And so as we do that, we nudge that forward, then that pushes the OH to the back. Just like we did before, same thing there. Now we have our isopropyl here. It's in the back. We want it down here now. We want the isopropyl down here where the OH is. Can you see that? OH is down low, and we have 2 things up high. We want the thing that's down low to be this bond, this 2,3 bond down low. So we want to basically switch places. So as we rotate, we're rotating the isopropyl that's in the back down to the bottom. And so as we do that, then the OH comes to front. And the methyl ends up in the back. Again, racemic. Because this is racemic, we end up with a racemic product. So this plus it's an enantiomer. So this is our syn addition product, and there was our anti-addition product on the previous slide. Questions on either of these, the syn addition or the anti-addition, the MCPA or the osmium tetroxide?
Professor,
Yeah.
regarding syn addition, anti-addition, so MCPBA will always give anti and OSO4 will always give a syn?
Right, because of where the oxygens are coming in. Oxygen as a nucleophile, and then oxygen as the electrophile. In 2 separate steps, it's always going to be anti-addition. Whereas both oxygens come in here, both oxygens come in one step here from the osmium tetroxide. So it's always going to be syn. Other questions? Okay. Let's move on to our ozonolysis reactions. How do I know it's ozonolysis? Because there's ozone here, right? O3, that's ozone. So remember, we don't have to know the mechanism for this. They do give you the mechanism in the textbook, so if you're interested, you can look at that. But what we do need to consider here is that we are breaking both the sigma and the pi bond. We're not breaking just the pi, we're breaking both the sigma and the pi. So if we number this, as we break that bond, we end up with a double bond now at the carbon that had the double bond to the other carbon. So carbon 1 here now has a double bond to oxygen. Now when we draw this, always draw your double bond to oxygen either straight up or straight down. As much as possible, draw your double bond to oxygen straight up or straight down. Now what else is over here on carbon 1 as a starting material? Remember that there's a hydrogen there? And so I'm going to draw that hydrogen in. I end up with an aldehyde here. Because carbon 1 had a hydrogen and carbon 2 on it, it keeps the hydrogen and carbon 2 attached, but now it just gains a double bond to oxygen. Same thing with carbon 4. Carbon 4 needs to have now a double bond to oxygen. What else is attached to carbon 4? Well, carbon 4 has carbon 3, and it has 5 and 6. I'm going to continue the zigzag pattern there. But here's 3, 5, and 6. I end up with a ketone. Just break the bond. Questions there? All right, then let's do the next one. So really just number the carbons. Where's the bond breaking? Number the carbons and keep everything attached. So I call this 1, 2, 3, 4, 5, 6, 7, and 8. I'm just breaking the double bond and the single bond between 3 and 8. So I'm going to have 1, 2, 3, 4, 5, 6. That looks horrible. Let's try again. So I have carbon 1, carbon 2, 3. 3 is still connected to 4, right? I'm not breaking the bond between 3 and 4. I'm not breaking any bonds here, 5, 6, 7, and then I end up with 8. None of those bonds broke. I just broke the bond between 3 and 8. All I did was break the bond between 3 and 8, but everything else is still connected. So then what needs to be on 3? Well, 3 needs to have a double bond to oxygen, so I'm going to go straight up. But 3 has carbon 4 and carbon 2 on it, so we know 3 would be a ketone. What's on carbon 8? Well, carbon 8 has carbon 7 and a hydrogen. And so carbon 8 still needs to have that hydrogen. We're going to draw that one in. We show the hydrogen when it's an aldehyde. That's one of our hydrogens that we don't assume, we just show it. So we end up with this thing that ring open, and we get an aldehyde and a ketone all in one molecule. Questions here?
Dr. Nalbandian?
Yeah.
So should we be looking for this type of a reaction anytime we see ozone in our...
Yeah, exactly. With every reaction, you've got to be looking for the pattern. And so yeah, the pattern is when you have double bonds, then you're going to break it. Now remember, ozone is a gas, and so in general, you just have a lot of it around. You just have a lot of this gas. You just pump ozone gas in, and you just have a lot. So if you have more than one double bond, all of them will react. If you have more than one double bond, all of them will react. All right, again, same reaction. We're breaking this bond. Let's number this. We're not numbering it for naming. We're just numbering it for keeping track of all of our atoms. So every atom needs a different number. So we end up with 1, 2, 3, 4, 5, and 6. 5 needs to have a methyl on it. And we have, in a separate thing, 7, 8, 9, 10, and 11. They all are bonded to each other. We don't break any of those bonds. So what are we missing here? Well, on carbon 4, we need to have a double bond to oxygen. On carbon 8, we need to have a double bond to oxygen. Carbon 8 had 7 and 9. It still has 7 and 9. Carbon 4 had 3 and 5. It still has 3 and 5. They're both ketones. Questions on any of these? All right, so again, no mechanism for this, just draw the product. So number everything and keep track of what should be bonded to what. All right, so now we're to our final section of material. This is our polymerizations. So our polymerizations, remember we get this long chain alkane, and the alkane is made from alkenes. So we look for our repeating units. So what's the repeating unit? Call it AB. 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 A is a CH2. B has these two groups on it. A is a CH2. B has these two groups on it. So that repeating unit is going to show up in our alkene monomer. Now, I might not always tell you it's an alkene, but it is always an alkene that is the monomer used to make polymer. Alkene monomers make polymers. Polymers are long chain alkanes. And we use alkenes as the monomers. So what is the repeating unit? AB, AB. We have this carbon that we called A and a double bond to this carbon that we call B. That is our alkene monomer. So A and B have a single bond between them. We give them a double bond. Now, what's attached to these two carbons? That needs to stay attached. What's attached to A? A has 2 hydrogens, so I need to still have 2 hydrogens on A. What's attached to B? Well, B has a methyl, and B also has this ester. This is my alkene monomer. This is the alkene monomer. So double bond, we have this double bond to oxygen, oxygen, methyl. This would be the alkene monomer here. So look for AB. What's your repeating unit AB? What's attached to A? What's attached to B? Questions here?
So you're basically just turning that carbon on carbon B into an alkene
Between A and B.
between A and B. Oh, okay.
So A and B is a single bond. We use those electrons that are between A and B to make this new bond between B and A of the next one.
Okay.
A and B was a double bond. We use those electrons to make the next single bond, to make the next single bond. So think back to our mechanism for polymerizations.
One quick question, Professor. So regarding the ozonylation reactions?
Ozonolysis.
Ozonolysis reactions.
Yeah.
Okay, so how do we know whether we will have a ketone or aldehyde?
Based on what is attached.
Uh,
Here's our mechanism for the polymerization. So double bond attacks one of the carbons, and then the electrons get pushed over to the other carbon. And so here it gets pushed to B because that would be stabilized. The intermediate that we get would be stabilized by resonance. Back to what you were saying, Ahmed. Why did I keep pointing out here? What's attached to carbon 4? What's attached to carbon 8? What's attached to carbon 8 here? A hydrogen and carbon 7. What's attached to carbon 3 here? Carbon 2 and carbon 4. That's how you know if you get an aldehyde or a ketone. You just keep everything attached. All right. Now on to, well, actually, let me tell you that this is the polymer used for plexiglass. This is that plexiglass polymer that is impact resistant. All right, so now we want to do the mechanism for this trimerization. So we want to have 3 monomers, but it's acid catalyzed, and we want to use 2,3-dimethyl-2-butene. So what does that look like? 2,3-dimethyl-2-butene. So we want to react that compound with acid. Middle of the double bond to the hydrogen. As we do this reaction, we're going to end up with a positive charge on one of these carbons. It doesn't matter which carbon gets the H in this case because they both have no hydrogens on them, right? So if I call this 1 and I call this 2, it doesn't matter which one. So here 1 got the hydrogen and 2 has the positive charge. 1 got the hydrogen, 2 has the positive charge. So what do we do now? We react these 2 together. So I'm going to call this 3 and I'm going to call this 4. So from here, the middle of this bond to carbon 2, here's my carbon 1, here's my carbon 2. Carbon 2 still has 2 methyls attached to it, and now carbon 2 is in a bond to carbon 3, which has a bond to carbon 4. Carbon 3 has 2 methyls attached to it, carbon 4 has 2 methyls attached to it, and now I'm going to give it a positive charge. This is a dimer. We have 2, right? We used 2 monomer units. We reacted 2 monomer units together to make a dimer. Now, I'm going to draw another one of those monomers, alkene monomers. 3, 4, I'm going to call this 5 and 6. So from the middle of the bond, again to this carbon that has a positive charge. Now I've reacted there where now carbon 4 has a bond of 5. And now between 5 and 6, there's a single bond. So this is really our trimer, but we had acid catalyst, right? This was a catalyst. So let's lose acid now to regenerate it. That's what we do for our catalyst. Where can we deprotonate? Well, remember we look 1 carbon away from the carbon that has a positive charge. So if we go 1 carbon away, here we are. The only thing that we can do is one of the methyls. There's no hydrogens on carbon 5. No hydrogens on carbon 5. So the only thing we can do is from the middle of the bond to the middle of the bond. So now we get this double bond here. So this is our final trimer where we regenerated our acid catalyst. So remember we were doing AB, AB, AB? Well, where's our AB here? A, B, A, B, A, B. That repeating unit, we're seeing it over and over again. Carbon with 2 methyls is A, carbon with 2 methyls is B. Carbon with 2 methyls is A, carbon with 2 methyls is B. This is A, this is B. 2 is A, B is 3 here. So we get this repeating unit. We have to catalyze the reaction. We start the reaction with acid. And so every time we're doing this, when you see this positive charge here, you know it was acid catalyzed. When you see a negative charge, you know it was anionic. If you see a radical here, you know it's a radical mechanism. So you can tell what happened in the beginning based on your intermediate that you get. But here we added in 3 monomer units. Here's 1. Well, I guess I should say, here's 1. This is our first one. Here's our second one, and here's our third one. 3 monomer units put together gives us our trimer. Questions on this?
I have a question.
Yeah.
Would you just leave the double bond on the terminal end then to finish it?
So that's how the polymer ends. You know that you're not going to have something that just has a positive charge hanging around. In the end, you have to regenerate your acid catalyst. So in the end, the polymer ends with 1 double bond. Other questions? So if it was a radical reaction, you know how to terminate radical reactions, right? 2 radicals react with each other. So maybe 2 different polymer chains that are building, they find each other and react. And so we just make a single bond there. So no double bond, just making that single bond. And then anionic, maybe we just protonate in the end. We add in some acid because we have the negative charge. We add in some acid, we protonate on the end, and that would end that, that anionic reaction. Any other questions?
Do you want to keep these polymer reactions or like polymer forming reactions at high or low temperatures to maintain the formation of polymers?
You actually do them at, a lot of them require high temperatures or kind of stringent conditions because alkenes don't react with themselves. But yeah, once you increase the temperature, that's when you'll see more, for this, you'll see more eliminations. So you do need like high pressure, sometimes high temperature. So it kind of depends on the reaction that you are doing, the specific reaction. But yeah, high temperatures will favor eliminations here. So for this reaction, you want to keep it low until you want it to eliminate, giving you the alkene product. Relatively low. Other questions? On anything last minute from chapter 12? All right, so we are at the end of chapter 12. Your problem set will be available. I think I had planned for 1 more day, so I'm going to make it available in a minute after class ends. So this will be due on Friday. So remember, every time we finish a chapter, your problem set will be due the next time we meet. So Wednesday to Friday for this one. Your exam is coming up over these 2 chapters. So make sure you understand this stuff really, really well because we'll have our learning assessments and our exam next week. All right, any last minute questions?
Sorry, I keep asking questions. For the oxycyclopropane, you attacked with the alkyl lithium on the less hindered side, how do you know again if it's less hindered versus more hindered you're attacking?
So, Liz, look at the syllabus. It's what the chapters that are on the syllabus. So for this, we are attacking the less hindered side because it is a neutral ring. So here we're thinking about sterics because it's a neutral ring. But here we attack the more hindered side because it was a positively charged ring. And so for that, we're really thinking about where, we're thinking more about like hyperconjugation, adding in electron density. This becomes more of a partial positive charge here. And so that's more electrophilic because of the positive charge.
All right, that makes sense. Thank you.
Uh-huh. Okay, you guys. Any other questions? All right, then that's the end. I will see you guys for lab today, tomorrow, and then we will begin chapter 13 on Friday. But again, that's not going to be on this next exam. We'll begin chapter 13 on Friday, and we'll just, keep moving along while you study and prepare for that exam that we have next week. All right? Have a good day, you guys. I'm praying for you can do this. Keep studying. Keep working hard. You can do this, though. All right? Bye, you guys. Love you.
Thank you.
You're welcome.
Oh, Dr. Nabon.